Okay, good morning. So today we will start to move on to the topic-based reliability phases and phenomena. So the first issue we will discuss today is the interface charge and the bias temperature instability, or sometimes we just call as a BTI. So this is the outline for the today's lecture. So we will talk about the basic oxide properties and also some of the charges and defect in the oxide, and in the end, the charge injection in the oxides. So first of all, we have to understand that if we have the MOSFET, and which of course the most important properties or the unique property for the MOSFET is that we have the silicon dioxide as a insulator. So if you consider the typical MOSFET, of course right now the technology has been advanced in the different way of the dielectric, but the one that is still most important is the one of the silicon dioxide. So this is still the very important one for nowadays the technology, not only for silicon. Sometimes in the other technology, we also will consider use the silicon dioxide for a certain purpose here. So therefore, we have to understand that if we want to have the dielectric being used in the transistor, what's a typical requirement for the gate dielectric? And first one is the dielectric has to be able to reproduce growth and also has a uniform thickness. So that's very important, especially if we move to the large wafer size beyond 8-inch or 12-inch, then the uniformity of the dielectric is very important. And then second one is that we expect no or very minimal charge or defect inside the dielectric. That's what we expect. And also sometimes we consider as a good diffusion barrier, because on top of the silicon dioxide, on top of dielectric, probably will deposit several different material, and the different material might cause a diffusion issue. So we hope that dielectric can work as a good diffusion barrier as well. And also, ideally, we should have the dielectric should have the property of no leakage current. But of course, it's not possible to have no leakage current, because based on the quantum mechanics, so we know that there's an issue related to the tunneling current. But ideally, we hope our dielectric can provide the function that highly reduced leak current, and also the large breakdown voltage and then very long time to break down. So that's what we expect here. So if we consider for the property, so this, the left hand side, this is a general requirement if we want to deposit a new material, no matter whether it is silicon dioxide or not, a new material for dielectric, we should all consider all these aspects. But now if we look at for the most important one and the very often used one, which is silicon dioxide. And generally, if we consider silicon dioxide in terms of the reliability, what we expect, first one, of course, we hope to have a good reliability. Usually we expect a very low leakage current. So we want to have a very low gate current here. So that's because once we apply the gate voltage here, for sure we will start to induce a certain leakage current, but we hope our silicon dioxide can allow us transistor to have very low leakage current. And second, we want the dielectric of silicon dioxide. If that should have a good reliability, we expect a very low defect. So the defect, we hope to have very low defect inside the dielectric. So this is because we should realize that every material should not be perfect, no matter for silicon or silicon dioxide or other material. So it always has a chance that the defect can be generated or be existed inside the dielectric. So we hope to have very low defects. And the last one is we want to have very low interface state. So the interface state is related to the certain defects in the interface, and because this defect in the interface becomes as a low energy state that the electron can be possibly flow in and trapping in here. So that's why we call this as an interface state. So these are the three general requirements if we want to have the dielectric that being with a good reliability. And also, here's some more information. The silicon dioxide is a non-crystal insulator, has a very high energy gap. Usually we have the energy gap around 9 electron volt. So that's a very large band gap for the as a silicon dioxide. And also one of the features for silicon dioxide is very easy to grow on silicon with a very low defect density, and also easy to integrate in the process. And conventionally, we have the hydrogen annealing, so the interface state can be electrical neutralized by using the hydrogen annealing. So that's one of the very often used process to reduce the interface state if we consider the silicon dioxide silicon interface. So sometimes we also call the interface state, it's just a name as a DIT, so that's an interface state. And also, silicon dioxide is very stable and insensitive for the following process steps, so that's why we really prefer to use silicon dioxide. And also, this mentioning the silicon dioxide is an excellent scaling possibility, but this now probably is not true anymore. If you look at the literature, time to time, of course, the semiconductor technology is evolving time to time. So with a certain time, what we understood before might change. Also, silicon dioxide now is not considered as an excellent scaling possibility, and also the next part, no real candidate for the replacement. Nowadays, we have a lot of the candidate that can replace the silicon dioxide for the certain consideration. But in general, the extraordinary property of silicon dioxide are the base of the success of the MOS technology. So the reason why that the MOSFET can be really fast, become the main trend, main dominant technology in semiconductor. One of the reasons is because due to the silicon dioxide, because we can easily grow silicon dioxide. Also, silicon dioxide material is very stable and very large band gap. So these all make the MOSFET as a very attractive technology. But nowadays, we still face several issue for the silicon dioxide as well. So one of the issues is related to the scaling. So if you look at if we have the silicon substrate here, as you know, the semiconductor has a trend, try to scale it as a smaller as possible, as a thinner as possible. So therefore, there will be the chance that one day we try to scale silicon dioxide below 1 nanometer. And in this case, once being moving to the status of silicon dioxide below 1 nanometer, we have the huge leakage current issue. That's based on the quantum mechanics. We all know that once the dielectric becomes very thin, then the tunneling current can be very high. So therefore, we have to come out with some other solution to avoid this high leakage current. And one of the very popular approach is we will put another dielectric on top of the silicon dioxide, try to reduce the leakage current. And in nowadays, another high K material, for example, like the hafnium dioxide, this is generally we call the high K because the dielectric constant is beyond 20, and usually our silicon dioxide only have a 3.9 of the dielectric constant, but the dielectric constant is beyond 20 in the high K material. And this is because we generally have the trend. If you look at the band gap versus the dielectric constant, we always have the trend like this. So that means in the case of silicon dioxide, here, silicon dioxide has a large band gap, 9 electron volt. But the problem for silicon dioxide is a very low dielectric constant. But now, if we try to use a high K material, for example, the hafnium dioxide, we have the more than 20 dielectric constant. But the issue for the hafnium dioxide is generally once we have the large band gap, always has a lower. Once we have a large dielectric constant, we always have a lower band gap here. So that's a general issue. So that's why we cannot only deposit a single high K, because a single high K layer only have very small band gap. So sometimes we need to compromise these two features. One is silicon dioxide that has a large band gap. Another one is a hafnium oxide. We want to have the function, the property of a high dielectric constant. That's why in the end, in the nowadays technology, we will very often to have this, what we call the bilayer. So that means we combine the one conventional silicon dioxide and another high K material is deposited on top of the silicon dioxide. So that we can combine the both feature of these materials here. And one of another reason that would be very promising to have the high K material as a dielectric, which is because if we look at the current equation, the drain current is proportional to our oxide capacitance, which is equal to our dielectric constant over our thickness here. So if we want to improve the performance of our transistor, which will be the higher current, so generally the approach can be either reduce the thickness or increase the dielectric constant. So that's why the adaptation of the high K material is very important, because in the end, we can either reduce the thickness or we find a material that has a large dielectric constant that can give us a great property to improve our current here. So that's the general background information. That's why after a certain moment, if you look at the semiconductor roadmap, you will see after a certain moment we start to see people in the industry will start to replace the silicon as a high K material. We will start to use a high K material, high K dielectric as a main trend in the semiconductor, because we can increase the current due to a high dielectric constant. But since the silicon dioxide is still the one of the most important dielectric, so we will still use the silicon dioxide as an example. But many basic understanding or theory that we use in silicon dioxide can be easily extended to the other material as well. Okay, so here is some property of the thermal silicon dioxide. So I think the most important one, this is table for your reference, but if you are in the future is mainly in the semiconductor field, you should at least almost remember the two important property of the SiO2, which is first one is a dielectric constant, 3.9. So this is a K value, and another one is energy band gap around 8 to 9 electron volt. So this is EG here. So this, for me, there's so many properties for the SiO2. The only two I remember by heart in my mind is these two. So I believe this is also very important, will be useful for you, because in the future, once we talk about other materials for the dielectric, we always try to benchmark the basic property compared to SiO2, and then we usually refer to what will be the K value for your new dielectric, what will be the band gap for your new dielectric. Therefore, you have to at least to understand these two properties for SiO2. Okay, so now we have to understand the ideal dioxide, which is defect-free. So we consider the ideal oxide is there's no charge in the oxide or no allowed energy state in the forbidden band gap of an oxide of silicon. And also, ideally, it's a perfect insulator. So there's no carrier transport through the oxide. But in reality, is that we have a lot of the defects and allow energy states inside this oxide here. So if you look at the left band diagram for the MOS structure, we have the metal here. We have the SiO2. We have the silicon here. So the first, basically, when we try to plot the band diagram, the one of the things, not only we have to pay attention to the band gap. Sometimes we also have to pretty sure about this value. So this is what we call the band offset. So the band offset is as long as the band offset is larger, that's good for us to have the certain advantage to reduce the low leakage current. So, as already described, we have SiO2 as a 9 electron volt. We have a silicon band gap as a 1.12 electron volt. So that means we have a huge of a very large band offset here. And if once we apply the gate bias here, from the semiconductor physics, we already know that once we apply the gate voltage for enough voltage larger than threshold voltage, we can start to have the electron formation in the interface between the dielectric and semiconductor. But if we have the certain defects inside the dielectric, and this will cause the issue of first, the electron might be jumped to this defect and then further jump out to the other side. So this will be the problem for the leakage current as well. So that's the issues inside the dielectric if we have the defects here. So defect and all allowed energy state exceeds the interface. So we have a certain interface might also have the here. This is all the allowed energy state in the interface. So these are the interface state. So basically we can expect that we will have these defects in the interface or the inside the dielectric, no matter how good your dielectric can be, even for the best one of the silicon dioxide. Nowadays, we still suffer this kind of issues here. And this will create the issue. That's what we generally call the trapping. So the trapping means that once we have the electrons being injected here, and then the electron might not immediately move away because the defect is kind of like the vacancy, so it's an empty seat, so the electron might be stay there for a while, and this will cause the trapping issues. So this trapping is because electrons are captured by the interface state or defect. So we might have the electron trapping here, but also electron trapping at the least interface as well. So both are generally will create the issue, what we call the trapping effect here. So now you can see the electrons will be placed in the region that should not be placed. So ideally, we hope the electron will be only existing here, or once the gate bar is large enough, then the electron will be injected all through dielectric and become leakage current. But nowadays, we found out that if there's a defect here, the electron might be sit here for a certain time, probably 1 minute, 1 hour, 1 day, 10 hours, we don't know. Or the electron might be captured in this region for a certain time, as like 1 month, 1 hour, or even 1 year, we don't know. So the problem is that it will become very difficult to predict how long the electron will be stay here, and after how long, probably after 1 month, the electron finally go out to the other side, and that's what we call the detrapping. So that's become the problem because we don't know how to estimate. We cannot predict our electrical characteristic because the electron can be seated, can be placed in this defect for a certain time, and after a certain time, the electrons can be moved into the other side. As you know, once we talk about the quantum mechanics, everything cannot be determined precisely. We can only determine the probability. But these things is become very complicated, as difficult to even estimate the probability. So that's a general issue related to trapping and detrapping. And also, because of these defects, we have the different charge injection and conduction mechanisms here. So, for example, ideally, our electron should be jump over this band gap, reach to the other side, become the leakage current. But now, because we have a defect here, so electron is no longer to move like in this way. This defect will change the conduction mechanism inside the dielectric. So now the electron can be first jump to here and then jump to there and become leakage current. So the conduction mechanism of this one is different compared to this one. So that will also cause the different leakage current. So that will have the leakage current issue. So that's the general issues if we have the defect inside our dielectric or interface. Okay, then first we have to understand, like the general understanding, what would be the typical charge or defect inside the oxides here. So first of all, we have these four different possibility charge. One is a mobile charge, second one is a fixed charge, the third one is interface trapped charge, and last one is a bulk oxide trapping charge here. So that's the general understanding. We have these four. And here is a schematic for these four different type of the charge here. So if we look at from the charge from the top to the down, the first one is this, the mobile charge. And the second one, which is an oxide trap charge, which will be in the middle inside the dielectric. And also, of course, you already know, inside the interface, in here, between the silicon and silicon dioxide, we have these interface trap charges here. So generally, we can estimate this by using the term of a DIT here. And also, last one, we might also have this fixed oxide charge, which is here. That's between our oxide and also our interface, and we have to take into account. This is the charge that we generally call as a fixed oxide charge. And one thing is interesting to know that is this is proposed in the 1967, which is even older than me. But nowadays, this basic understanding of all these four charges exists in the semiconductor dielectric is still quite true. We still use this concept to look at for the different dielectric, different process. So this is pretty like the mechanism or the basic knowledge that have been proved again and again. In the end, we found out that this is knowledge is actually quite true. And because of all these, the charge, in the end, this all charge will for sure to influence our threshold voltage, as shown here. This is a general equation. In this topic-based lecture, we will mainly to talk about the physics, understanding, and phenomena. But we will talk about the equation derived, because these are the equation has been derived for more than 30 years. You can easily find a lot of the reference on the internet already. So the threshold voltage is related to the ideal threshold voltage. The metal semiconductor Wolf function also will be influenced by these three terms: fixed charge, mobile ions, and trapped charges. So that's become the issues, like the why. For example, you can, in the one transistor, ideally you can have the hand calculation to calculate your threshold voltage by consider the ideal threshold voltage plus a metal semiconductor Wolf function. But once you really fabricate those transistors, you measure the threshold voltage, you might find out that the reality of the threshold voltage is completely different from your estimate value. And this is because all these three terms also will create the impact on our threshold voltage. And these three terms are mainly come from the materials property, the process, and so on. So now we will look at them one by one to understand what will be the typical cause for this charge. The first one we'll talk about is the mobile ionic charge, which is mobile ions. So these are the impurities such as shown here. And the origin can be is mainly related to the sum of the process, or it's not related to the semiconductor. It's physics, mainly related to the environment issues. So for example, we have the origin of the lithium that's mainly come from the vacuum pump oils here. And we also have might be this sodium, that's because of that's already very common in the process to have the contaminations here. And typically, these will lead into the impact of the move with the polarity of electric field that's cause IV hysteresis and reliability. So the ionic impurity can be moved with the polarity of the electric field. So this actually means that this will be influenced by the bias. So the polarity electric field, that means you give the positive or negative bias, that will be influenced on this impurity. And also this impurity will be influenced by the temperature as well. And one of the typical phenomena that we can see from this issue is if we look at for our IDVG curve here. If we have the IDVG curve here, we do the sweep from the right and come back. So we do this sweeping from low voltage to the high voltage, from the high voltage to the low voltage. Then we will see this threshold voltage change. So that's we call as a hysteresis. So actually, every semiconductor device should always have a hysteresis, just related to how large of hysteresis can be. And in many of your own research related to semiconductor, if you try to sweep your device in this way, you always can see the hysteresis, like shown here. So this for sure will cause a certain reliability problem because our threshold voltage is not constant, it's not stable, it's a change with respect to the time and with respect to the bias here. And one of the typical way we do the measurement is by consider the bias, temperature, stress. So that means we stress our device with a different bias and temperature to see how this threshold voltage shift. And then we can estimate the flat band voltage shift. The flat band voltage shift is because we can do this on the CV measurement. So now, once we have a flat band voltage shift, we can start to estimate the mobile charges by consider our capacitance times our flat band voltage shift. So that's a very basic approach to estimate the amount of the mobile charges we have. Of course, there's some general solution for this. So we have to use a certain different gas in the oxidation. Also, we need to further optimize our cleaning process. And the next one is oxide phase charge. So this oxide phase charge, which is a positive charge due to the structural defects near silicon dioxide interface, that's a transition region. So as you know, we have a silicon substrate, and how do we form the SiO2 is that we will put it in the certain thermal tube, and then we will have the oxygen flow inside, and the oxygen can start to react with the silicon and gradually to form the silicon dioxide. Of course, this oxidation process depends on the oxidation ambient temperature, cooling condition, or silicon or retention. So we might start to see there is a structural transition between silicon and silicon dioxide. And also, they have the chance to exist non-reaction silicon ion in the SiO2 layer. That will cause this fixed oxide charge here. And some of the popular approaches, for example, we use a dry oxidation, or we use a dry nitrogen or argon. We do some of the post oxidation annealing. This information might not be completely true right now for your technology, because this is highly depends on your substrate, depends on your temperature, and depends on your oxide thickness. But this is just for your information that in the past, people are very used often to this one to reduce the oxide phase charge. And this is one of the experimental results here. So ideally, this is oxide phase charge versus temperature. So we can see once we put the oxidation condition as being inside the dry oxidation, and we increase annealing temperature, then we can see our phase charge is reduced. So that's one of the experimental results to prove that the phase charge can be reduced if the process is correct. And one of the very often measurement techniques to estimate the oxide phase charge is we generally will use a flat band voltage shift. That's a VFB. So we will use a CV to estimate the VFB, and then we can use the VFB to calculate our oxide fixed charge as shown here. So ideally, we have this one. This is ideal CV curve. And then if there's a positive oxide charge, then we can see our CV curve will shift to the left. So once we have the negative flat band voltage shift, that's always indicate we have the positive oxide charge. On the other hand, the idea is here. But now, if our CV curve is shifted to the right, that means we will have the negative oxide charge as shown here. So that's most of the students, when you first time to learn the flat band voltage, usually is very confused because of sometimes not being easy to know why we have to learn the flat band voltage. Of course, flat band voltage is the first important function for flat band voltage is we have to use to calculate the threshold voltage. If you look at the inside again for how do we estimate flat band voltage, the concept we have to bring is first we base on flat band voltage, then we start to step by step to calculate the threshold voltage. But usually we won't calculate threshold voltage unless you are the guys working on the like a modeling or analytical analysis, try to develop some equation to the modeling. So you will probably do some hand calculation to estimate the flat band voltage. But on the other hand, another very often used the timing that we will use a flat band voltage is when we do this fixed oxide estimation. So in this case, we will very often to estimate the CV. We will use the CV and to estimate the flat band voltage. So that's to be honest, very often used. And then in all kinds of semiconductor material, and also the analysis here is not that difficult. It's very straightforward. And another thing we just want to stress here is that sometimes you also will get confused what's the difference between the flat band voltage and threshold voltage. And to my understanding, when we consider the flat band voltage is because we use a CV. We use a CV measurement, then we will estimate our flat band voltage. But this flat band voltage is certainly correlated with our transistor as well. So the flat band voltage being estimated inside the MOSFET almost identical to the threshold voltage we are estimating in the IDVG curve. So I think these two terms are most equal to each other to give us of course the quantity might not be the same. The absolute quantity is not the same, but the shift, this shift to tell us is the same meaning. So wherever you have the positive flat band voltage shift, you always have the positive threshold voltage shift. You have the smaller VFB shift, you always have smaller threshold voltage shift. Okay. So the next is an oxide trap charge here. So we have the positive, we might have the positive. In the past, in the beginning, we think it's only have the positive, but in the end, the knowledge is being revised. And now we also understand that it's possible to have the negative charges in the oxide due to the trapping electron or holes here. So if we talk about the oxide trap charge here, we have the two. One is electrons here. This is electron trap are distributed through the oxide layer, and we might also have the hole trap near silicon dioxide here. But of course, this is purely based on the silicon knowledge, but nowadays, we do see the electron and hole trap inside the bulk oxide, but it doesn't mean that this electron and holes always in the position like mentioned here, that the hole will be only in the interface, but the electron will be in the oxide. But actually, in reality, electron can be also exist in the interface, and the hole can be also distributed through the oxide layer. But the most important is what you have to know is that how this will influence our characteristic. So generally, if we have an electron trapping, we have the positive shift. If we have the hole trapping, we have a negative shift. This is very important concept here, because this can help us to understand in our device we will have the electron or hole trapping or not, because we can look at the electrical result shift to do the first estimation. In the past, it's always a semiconductor that only appears either electron trapping or the hole trapping, just one case always. But nowadays, our semiconductor device is become way too complicated. So you will very often to see in the nowadays device, we both have the electron and hole trapping at the same time. So you will see sometimes your threshold voltage is starting to shift to the positive, but after a certain moment start to shift to negative, because we have start to have the whole trapping happen after certain conditions here. So the origins can be related to the first one is the process induced. This is mainly like the process related. So we have the damage during the process, or we have this is ionization, radiation, charging effect during the plasma process. So the plasma process is also one of the possible reasons that cause the defect in the end to cause the trapping phenomenon in our dielectric. And what we actually more interesting to understand is the second one, which is a defect generated during the operation. So this is something that we will talk about details and later. For example, high electric field, that will also generate more defect. Hot carrier injection, that will generate the defect. Or the ionization radiation will also generate the defect as well. So the oxide trap charge, as already said, sometimes we also call this as a box oxide trap. In general, the oxide trap charge or box oxide trap is a trap where we consider in this region as well. So this is a schematic which consider all kinds of possible the defects in the one metal semiconductor, dielectric semiconductor. So this is what we call the bulk region here. So the bulk oxide trap is a electron trap and hole trap located away from the silicon dioxide interface here. The reason that why in the end that the people start to put a more and more complicated name. If you look at for the 30 years ago, 40 years ago, the literature, everyone is only talk about interface state. So at that moment, we only believe the interface trapping is a main issue for semiconductor degradation, is a main issue for our threshold voltage shift. So this is the interface state. is here. So these are the interface state. But the problem is that as a technology evolution, in the past we have very thick dielectric. We have the 50 nanometer SiO2. So wherever you apply the electric field, if you divide, wherever you apply the bias, if you divide by electric field, it's always very small electric field. So it is true at a moment we might only have electron being trapped in this interface as well. But once we start to scaling our dielectric from the 50 nanometer down to 5 nanometer and beyond, and also, well, if you look at the same operation voltage, but if you scale from 50 nanometer to the 5 nanometer, actually your electric field is increased 10 times. Of course, we can reduce our voltage operation. That's the purpose why we do the scaling, because in the end we want our device can be operating the low voltage, but that still causes a relatively high electric field. Then people start to feel that the pure mechanism with only considering the interface state is not enough to explain what we see in the reliability. We still see the threshold voltage shift, but we cannot understand comprehensively if we only consider interface state. That's why people start to propose that, okay, nowadays, this trap here is not enough to support our understanding. So we start to come up, the traps also might be happen a little bit further inside the dielectric, but not that far. So that's, we generally call this as a border trap. So the border, it means that this is the trap, like you have two countries in the middle of two countries, usually we call the borderline, that's a 边界. So the border trap, that means that it's close to interface, but not exactly interface. It's a little bit far inside the interface, so that's what we call the border trap here. But also, again, once we come out with a border trap, it's fine with a certain time period. But as long as our technology start to evolving again, we still feel, okay, now there are lots of phenomena cannot be explained by purely consider the border trap or interface state. So that's why in the end, we have to include the bug here. Bug trap here. So that's why in the nowadays understanding, like what we have the defect inside the semiconductor, basically what we know now is that we think everything, everywhere is a place for the defect. Everywhere can be possible trapping, because in the beginning we only see there's only defect in the interface, and after a certain while, no, we feel like, okay, the interface state is not enough, so we propose there's a region very close to interface, that's a border trap, and this theory is fine with a while, but after a certain moment we start feel like, okay, that's not enough, we still need to include another defect inside the semiconductor. So in the end, the conclusion is that inside the dielectric, everywhere is a defect, just has a different meaning. You have an interface, you have a border, you have a bug. But the idea is that wherever the region inside the dielectric always be possible become the trapping locations here. So that's a themes here. So we have the this is we have the electron might be trapping by the interface state, or we have the electrons might be trapped inside the border region. Also, we have the electrons might be trapped in the bulk region as well before reach to the other side become the tunneling current. So actually there will be the different region that the electron can be trapped here. But of course, how we can make this theory is, of course, is based on some very scientific proof. For example, if we have electron trapped in the bulk region, usually we have very huge time constant. So the charge is almost fixed. So that means once your electron being trapped in this region, probably the electron will be stay here forever. So that becomes almost a fixed charge. So that's why people will come out the trapping inside the bulk, because of if only trap in the interface state, it's very shallow. So ideally, the shallow trap should be immediate to detrapping. So time constant is very small. But if we trap it inside deeper, the time constant will be very, very large. So this means our detrapping is slow. And this, of course, will affect on long-term stability. Especially, we can always consider this is like the permanent trapping carriers. So the permanent trapping carrier will completely change our device property. So this will cause a long-term drift and eventually a device the values here. The why we can have this conclusion is usually if you look at the threshold voltage. If we have the plot here, this is a VTH versus a time. As already mentioned, like when we talk about reliability, everything is related to the time factor here. So initially, we have the threshold voltage here. If we start to apply the positive gate bias, we start to see our threshold voltage shift. So that means our threshold voltage become larger. But if this is mainly due to the interface trapping, this is due to the interface trapping effect here. Then what we expect is that now we consider in the time that in the status that we don't provide any bias. That's a VG equal to 0 volt. So that's a very often used technique when we try to understand the trapping effect. We do the stress, and then after stress, we don't give a bias. Of course, we don't give a bias. The official name that the status we don't give a bias is we call the recovery. So this is a recovery understanding. We try to look at the recovery characteristic. Of course, this is interface trap, so we expect that the trapping time constant is small, so you can trap in, but immediately after certain you can see the electron detrapping. So once the electron detrapping, we can start to see our threshold voltage gradually move. So that's why we call this testing as a recovery, because now we see the recovery of our threshold voltage here. So this recovery is a phenomenon related to the detrapping. So I can fully understand like detrapping sometimes is a very the word meaning is not precise. Also, it's sometimes it's an effect you cannot visualize. You cannot visualize electron being captured it's difficult to visualize this phenomenon. It's not like it's a completely open short or complete breakdown. You see the certain damage. So the trapping effect is happening inside the dielectric, so you cannot visualize the effect. But what we usually do is we will come out with the electrical characterization, try to visualize this effect. So this is one of the examples. We will characterize threshold voltage. We do the stress, we see the threshold voltage shift. But now we do the recovery, we see the threshold voltage shift back with a very fast time, timing. So that means this is a very shallow trap. So that can be due to the interface trap. But on the other hand, what will be the happens if we trapping inside the fix, inside the bulk oxide? So again, we have the VTH shift here. We have the time here. And then, first of all, this is our fresh threshold voltage. We do the stress here. This is a situation we have the VG apply. And this, if this increase is due to the bulk trapping, then once we start to do the recovery testing at VG equal to 0 volt, we will see the threshold voltage shift will be stay here. There's no recovery. There's no recovery effect here. So that's why they say the charge is almost fixed here, and the trapping is very slow, and this will influence the long-term stability and the permanent trapping carrier. So this case will always consider this is a permanent degradation. So these are the two extreme cases. One is purely trapping interface. You will see very fast trapping, very obvious recovery. And another extreme case that your trapping is mainly inside the dielectric as a bulk trapping. Then you will see the permanent degradation. You won't see the recovery. But in reality, it's between these two. It's always trapping, and then you see the partial recovery. Certain part, you won't see any you cannot see the fully recovery. You only can see the partial recovery because it's a combination between the right and the left. Okay, so once we talk about the oxide trap charge, you also have to come up with a certain mathematical way to estimate this trap, because we cannot always use a very vague physics concept say, yeah, there's a trapping inside the dielectric, but we had to come up with a way how to quantify this the trap here. So one of the way to quantify is that the trap is always being characterized by trap energy level and also the capitular cross section. This is pretty important. If you are in the reliability field, you definitely will see this term very often. So the idea for the trap energy level can be understood from this schematic as well. So once we have the defects, let's say if we have the defect here, so then we apply the parity gate bias. So we start to have the electron in the interface, and the electron will start to move in, but suddenly if there's a vacancy here, then electron will start to fall into this energy well and start to stay here. So therefore, one of the ways to characterize is consider this energy level. trap energy level. So as you now can see, if your trap energy level is larger, that means the position for the trap is deeper. So that also fits very well that some of the trap have very long time constant, because you have a deeper, that means you have the difficult to come out. So in the end, we use this trap energy level to characterize. And another is what we call the capture cross-section. So capture cross-section is a term to describe the probability that trap capture, the trap center can capture electron or hole. So it's mainly related to probability. So we have the several different cases here. If we consider it's a neutral trap, that means this trap is neither very likely attractive, nor likely to repulsive. That's what we call neutral trap. So the capture cross-section will be valued between 10 to minus 14 to 10 to minus 18. But if our capture cross-section is larger, like in this case, that means this trap is like it's attractive. This trap center is attractive. So you have the electrons here is likely to be attractive in this trap center. On the other hand, if we have very small value, that means this is a trap that have the repulsive. So that means the electron here is unlikely being trapped here, because this trap center exhibit as a repulsive characteristic. And also, once we talk about the electron is being captured by the trapping side here, it can be discharged by the different phenomena. The discharge here is also has the same meaning for the detrapping. So here is a several possibilities that how the electrons being detrapped. The first one is called the phonon-assisted detrapping, or sometimes we just call as a thermal detrapping. So that means you have the electrons here start being trapped in this trap center, but now will be detrapped. This is detrapping. So this is related to thermal detrapping. So I think it's pretty easily can be understood. The thermal detrapping, that means that you try to heat up this sample, and then the thermal, once you heat up, you will provide thermal energy for the electron here. So electron stay here will be excited due to the thermal energy, so will be likely to come out again. So that's what we call the thermal detrapping. And second one is due to the photon. So photon is related to the illumination. So once you have a light being injected in the region where we have the traps here, so of course the electron will gain additional energy due to the light. So that's why the electron can come out again. Also, the one is what we call the field detrapping. So field detrapping is also, it's not that difficult. It's just because of you have the electron trap layer, but now because you apply the additional bias, so that's why you have additional bias. So then your trap in electron will be gain additional energy. So this tunneling can be happen as well. And last one is what we call the impersonalization. So impersonalization, it means that we start to generate the electron and hole pair. So this is a hole, will be generated due to implantation, and we have the electron here. So electron and hole will be recombined. So then our trapping electron will disappear. So again, these four actually, if you try to think about the physics mechanism behind, it should not be very complicated, because the first one is related to the thermal. So once you heat up your device, for sure your carrier will gain additional energy, so you can have the thermal detrapping. Once you put a line to shine on your sample, your trapping electron will gain energy again. Or you apply additional field, or you have the implantation that causes the hole to recombine electrons here. So these are the four possible mechanisms leading to the discharge or the detrapping effect. So if we try to calculate the trapping or detrapping of a thermal carrier on the trapping side, can be described by consider this first order rate equation. And here I won't go into detail, just want to let you know that the previous discussion, what we have been shown here is all reflect here. The first one is the thermal capture, the photon detrapping, phonon detrapping. These are all the phenomena we have talked about previously. In the end, will become the results that leading to the dNt over dt. That means a time-dependent field trap density. So that means the time-dependent field trap density is all consider the three effects here. And the importance for this calculation here is mainly to use to estimate the capture cross sections here. But if you need it, you can come up later for your own research. But in my experience so far, I haven't had a chance to calculate the capture cross section in my own research so far, because basically we all assume our capture cross section are in the neutral trap because to simplify the mechanism. But of course, if you are, once you future, because that's only related to my research, but probably your research is more advanced than what I did, so probably you need this equation in the future. Okay, so then last one is the interface trap. So interface trap is a defect near the interface that's already said that it can be characterized by trap density, DIT, that's we call interface state density, and these also related to the acceptor or donor type. And also, this can be slow and fast interface trap, can exchange charge with silicon band on time scale of picosecond to hour. So that's pretty important, because later on, the fast trapping detrapping causes a problem for the very precise estimation and modeling. So we will talk about this later. And the interface charge will affect on CV, transconductance, leach current, noise level, and usually we can estimate by CV or GV. GV is a very famous the method, how we call the conductance method. And the origin of the interface chart is, for example, the dangling bond at the silicon dioxide interface, but that's only limited to the SiO2 Si interface. So that's why the reliability is important, because you know nowadays we not only use silicon dioxide, we use very complicated dielectric, and sometimes we are not only use the silicon substrate, we use a 3.5, we use a 2D, we use a whatever. So every different dielectric, different substrate always cause again the interface issue. So we need to spend the effort again to understand. And defect generated is by the certain injection carrier or radiation impact radiation effects here. And then in the past, this is only limited in the silicon. We very often use hydrogen annealing to mitigate this interface charge issue. But if you are now working in the silicon, this is probably will not work for you. Okay, so that's a short summary. So charge at the interface charge is related to the charge at silicon dioxide silicon interface. The first reason is the dangling bond. So we have the silicon hydrogen dangling bond. And we used to have a low temperature hydrogen annealing, and that's a very special term for this process that we call the forming gas annealing. Now we have to understand what's the difference between the acceptor or the donor line. So the left hand side is something already shown that this is a typical Venn diagram between the metal, insulator, silicon, and we all know there's an issue here that we call the interface. And this is the interface state, and we characterize this as a DIT. But in consider the interface state, we have the two types of interface state. One is called the acceptor-like. Another one is called the donor-like. And there is a definition for the acceptor-like. So acceptor-like is neutral when empty, but now this will become negative charge if there's an electron occupy the state. That will become the negative charge. So this is the same like this one. Now you have to start to put some imagination, because this is the graph that combines the Venn diagram, also the trapping side. So first, where's the Venn diagram? This is Venn diagram. This is the Fermi energy, right? This is our EF. So means this is a EF inside a certain semiconductor material. But now, if your trap level is here, then in this case, your EF is below your trap energy level. So this is usually we consider as a neutral. Because below EF, that we have the electron. Above EF, we don't have electron. So now your trapping side is above EF. So that means your trapping side will not be able to access electrons. So that's why your trapping side is empty now. So that's what we call as a neutral. But on the other hand, if now you do something and then your EF is moving above your trapping side. So as I say, below EF is a region we have the electron. So now electron has a chance to start to access this trapping side, and we have the negative charge here. So similarly, we can have another case called the donor line. And donor line is just a completely opposite concept compared to acceptor line, where it's a neutral when full, but a positive charge once we have electrons leave. So now this can be also understood by this one. So by definition, neutral when full. So this is now our EF is below our this is the EF is below our trapping side. So that's this is case positive charge if we have an electron leave the side. So this will have the positive charge. But based on the definition, this is neutral. Because now you can think about this is the initial has a positive charge here, but once our EF is above our trapping center, you have an electron will be recombined with a positive charge and become the neutral here. So these are the two different type of the trapping. One is the acceptor, one is the donor. So the acceptor in the initial is empty. So once being charged, it has a negative trapping electrons layer. But the donor-like is the initial is a positive, but once being charged, it becomes a neutral. Okay, so here is a summary for the different kind of the oxide trap that we will face in the semiconductor. The first one is a mobile oxide charge here. So you use the bias temperature stress to understand, and also the oxide trap charge here can be used the several different. This is etch off, so to etch away, or we use a photo IV to measure. So we won't talk too much detail because of in this class I will focus on the issues related to this one interface charge that will be happen during the interface charge here. But anyhow, all these trapping charge will lead into the general issue of the bias temperature instability. So, because as I already mentioned, the knowledge of semiconductors is being developed time to time. Also reliability as well is being developed time to time. So in the early time, we only consider interface trap charge. Sometimes we consider mobile oxide charge. In later time, we start to have the oxide trap charge. So if you don't have any similar experience in this field before, you will feel like the knowledge here is a little bit discrete. It's not very consistent because sometimes we only mention interface trap charge because if you look at literature, there's a part literature. If you don't try to understand from the long history to the now, then you will get confused because of some literature only talk about interface trap charge. Some literature only talk about mobile charge. Some literature only talk about oxide trap charge here. But if you look at the recent, like the 10 years of the literature, what we actually do is we just try to mix everything, because everything in the end will always cause our electrical shift that's related to this phenomenon, bias temperature instability. So in the end, we just try to wrap out everything and we put it as a name. That's what we call the BTI, because the BTI is a term that generally includes all the phenomena we see here, all the shift, all the trapping, all the detrapping. We just give another bigger name, try to put everything include this. That can help us more easily to understand. Then you won't be confused at what's the correlation between the interface charge or the oxide trap charge, why the characterization is different. Because now the overall goal is try to understand the BTI, and BTI can be all related to all these terms. And the reason why is because of the knowledge is developed time to time. The understanding nowadays is completely different compared to 10 or 20 years ago. So we expand our knowledge base, and then we have to give a more general term to include every effect. So that's what we call as a BTI. Okay, so we will take a 10 minutes break and we'll come back later. 对，
会影响到reliability之类的。
对。
如果今天是用2维材料做基底，那它是覆盖的氧化层一样会有那些缺口。
会啊，一样会啊，你没办法长 SL2，你没有其他 LD，只要有不完整的界面、不连续界面都会有 reliability 问题，都会有 interface 这个 charge 问题。
那可是以好解释是2维材料来讲的话，它长 oxide 上去是会一定会比 C 感到麻烦的。
会啊，非常麻烦。所以因为它的见解不一样，它表面见解完全不一样。
所以通常来说，因为其实中我刚好在做另外一个报告，然后只是我找不到说，因为好像跟很多 paper 很难写什么，就是他只会写到说，可能用基底材料做的元件，不管是电解件还是什么，它的reliability都不好，只是都要说它的不好是指。
你就查一下，你查那个 BTI 2D， 就可以看到非常多的材料，非常多的 study 这一块，对，都show它的 BTI 是有很大的问题。对。
好，谢谢老师。
这礼拜有要讲这个吗？有，公司那个，而且老师你上网找，我会觉得有点奇怪。
小孩啊？对。
如果发现很多IG的地方会到，但是不算，有可能会发生。可是因为IG就是他们的有可能对。但如果我想说，如果是其他放出来其他地方就会怪怪的。对，因为他说 IG，但是他也有回到我的形象。可是我在想，有可能是他自己。对啊，所以我觉得那我们就接下来对，我们会做step。那这样的话，就是像我们在做的话，我们还要观察要么就是对，然后先压一个。到位。这个 BT shift，
对，
它这个是算是
permanent shift 这一种 case。
不一定，不一定，其实没有完全的情况下是 permanent 或者完全，大部分其实是介于就是有一半是 permanent， 一半是 recover。
那如果说我WT 已经测完了，
对
shift，
对，
那应该是已经 permanent。
没有，可是因为 WAT 的测前可能是你的元件，取决于你它是多少时间被 stress 完。对，如果它是马上 stress 马上测 WAT， 那它这可能就短暂。但是你要知道它是不是 permanent， 你可能要把它放一阵子，比如说放1个礼拜再来测一次。对的，或者你要设高温，看它会不会加速它的。
如果假设它是 permanent，
对，
那现在的 solution 是照光吗？还是说温度？
可是通常有 permanent 是不好的，所以我们的 solution 不是说利用这个照光或是加热让它恢复，是我们要想办法让它不是 permanent。对，那照光或是恢复只是让我们知道它的机制，因为知道它的机制，你才有办法算它的 energy level， 知道 energy level 才有办法知道说它可能跟哪个 process 有关。对，比如说你 thermal 或者照光，你打一个 EEV 的光，你就看到它完全 recovery， 你就知道这 trap energy level 是 EEV， 那你就可以知道说我们就可能思考像到底哪一种会可能要查文献或做材料分析，去看它里面的键解哪些会导致它会 EEV 的这个 trap。对。但最终目的当然还是要把它去除。对。
那如果是我用那个有 fermi gas 的那一种来练，也是属于，
也是一种，它是一种 process 去想办法修补你的界面。fermi gas， 对。
但是不一定回得来，对不对？
我只能说可以把它降低。对。它这种要分2种情形，一种就是说我们知道它是会有 trapping，然后我们经有一些这种方法去了解它的机制，然后最后再想办法从前端的 process 去改变之后，看这个 detrapping 的机制是不是会被改变，那代表我们的 process 就对这个有用，那这样子我们才可以找出一个 hint，去从 process 的角度。那 forming gas annealing 就是一种方法。对，然后第二个就是你要避免这个 bias。如果你就发现说我这个 bias 永远造成 permanent shift，那我就只能降低 bias， 就代表那个 bias 就是你的帮的，你不能超过那个 bias。对。
谢谢。
其实意思是说，你就是假设它就是这是一个 forbidden band gap， 对，然后这是 EC， 这是 EB， 对，那通常我们就是 EF 以下才可能会有电子，对，所以先从正常图这样解释，你的这个 EF 以下的时候是没有电子的，然后你的这个 trapping side 就是空的，对，所以当你 EF 超过这个 trapping side 的时候，你电子就可以 S 到这边，对，所以开始就会就是变成 negative charge。对。那这张图的话比较好解释，其实你就把它反过来想，它一开始是一个正电，它是一开始是在没有 trapping 的情况下是一个带正电，但是你 EF 大于这个 trapping side 的时候，你电子就可以去进来，它就综合这个，然后就变成空的。对。
所以它这个 EF 是去外加的吗？还是它这个
就 EF 就是跟你的 VG 有关。对，你加 VG 它就会调动它的 EF 在它的 band gap。对。
那我想就是那这样子，这个 infiltrate 跟fermi
有关系啊。fermi level pimi 的意思就是大概就是讲说，因为你的这个 trap 太多了，多到你的 EF 没办法自由的调控，它就像是一个钉子一样把你拼住。对。所以你的假设我们从这边到这边，假设是 VG 加个5伏，就可以自由从这边移到这边来。但你 fermi pimi 就是这边低费太多，你加5伏，它是移动到这边。
它就已经没有办法，因为你外加了电。对，
所以你 fermi pimi 为什么时温会变差？你的电子抗顺能力会差，因为它就是被这个低费都抓住。对。所以其实是有关系的。
所以它那个 fermi 就其实就是因为我这边 interface 这边的低
费太多了，对，所以导致你的 EF 不能很自由的移来移去。对。 Okay, so one of the issues for this interface or dielectric trapping is because we have the electron moving inside to the dielectric. So first of all, we have to understand what would be the mechanism that can cause the charge injection in the outside. So we have the several mechanisms here. First one is a very famous that we call the FN tunneling. Second one is the direct tunneling. We also have the hard carrier injection. So these are the very popular phenomena that we will see in our semiconductor device over and over again. So first one is FN tunneling. So the FN tunneling is a mechanism that the quantum mechanical tunneling through the triangular barrier between the silicon and then the outside conduction band. So if you see this band diagram as shown in here, so this is a situation where we start to apply the party gate bias in the right hand side. So once we apply the party gate bias, for sure you will start to pull the band diagram downward, and we start to have the electron. The electron here will start to see the small barrier because original the barrier is here. So there's a very thick barrier. But now we apply the positive gate bias here. Then the electron, the barrier that electron seeing here is become the triangular barrier as shown here. And based on the quantum mechanism, we understand that once your barrier becomes thinner, once you have the smaller barrier, the probability of electron tunneling will increase. So that's why now this is become the triangular. So the electron can have the chance start to across this barrier and reach to the other side. So this is a phenomenon we call the FN tunneling here. So once electrons are in the outside conduction band, they travel with relative high mobility to the anode. This is anode. And so substrate current start to follow for the fields about 6 megavolt per centimeter. And one of the features for this tunneling is that the tunneling in itself is independent of the temperature. So that means this is not related to temperature, but however is related to our phi s here. So phi s can be seen, the equation. And then the right hand side is a figure with 9.7 nanometer. Once we apply the gate bias, reach to the certain term, we start to have the FN tunneling effects here. So usually when we try to characterize the FN tunneling, or how do we prove that there's a FN tunneling, we will try to plot the J over E squared versus 1 over E. This is because of based on this equation. And if the result gives us a straight line as shown here, then that means that the conduction mechanism here is likely due to the FN tunneling here. And also in the junction, we have the issue, what we call the barrier lowering effect. If you don't familiar with barrier lowering, then you have to look at the semiconductor physics book. There's one specific chapter talking about barrier lowering. So once we have the barrier lowering effect, so that means the barrier is become lower at this point. For sure, once the barrier is reduced, we expect the electron tunneling can happen. The probability for the electron tunneling is increased. So that's also will influence the FN tunneling as well. And the next one is what we call the direct tunneling. So direct tunneling, as you can see here, this is because now our dielectrics become very thin. So it doesn't matter whether we need to have the triangular barrier or not. The electron can already direct tunnel to the right hand side, even it's not through the triangle barrier. It's just a typical tunneling through the whole barrier, and that's because due to the very thin dielectric. So direct tunneling is a quantum mechanical tunneling through the trapezoidal barrier between the silicon conduction band. So this is a trapezoidal teasing, trapezoidal barrier here. So in anyhow, the short summary is, if we talk about the FN tunneling, we only consider the case with a very thick dielectric. But now if we consider direct tunneling, this is a case very often happen in the very thin dielectric. And then the equation is shown me here, and this is one of the example that with 2.5 nanometer, we can see the current increase very fast. So now if you look at in this dielectric thickness with apply also VG 1 volt, the current is already reached to 10 to minus 4 amp. So that means the direct tunneling is a huge issue in the thin dielectric as a leach, because the leach current is increased very fast. And here is another very clearly evidence that related to the direct tunneling. This is the figure here is a little bit vague, not very clear, but it's come out with a very famous literature published in 1997. This is from the Professor Yuan Tao. So if you are in the field, you probably already seen. He has one book that's very famous, talking about the CMOS scaling. So at the moment in 1997, people already start to discuss the scaling issues here. So you can see this is a dielectric thickness. The unit here is an angstrom. So from the 36.1 angstrom scaling down to 10 angstrom here. And then the leach current is increased 10 times order. So leach current is increased 10 times order. So this is a clearly evidence that once we continue to scaling of our dielectric in the semiconductor, we face the issue of a huge current due to the direct tunneling. So direct tunneling current at 1.5 electron volt increased by 10 order of magnitude, when the thickness just decreased from 3.5 to 1.5 nanometer. So that's why, as I already mentioned in the early of this class, we mentioned about the high K dielectric. That's why we need to have a high K, because the reason one would need to have a high K is also mainly come from this basic equation that the drain current is proportional to our oxide capacitance, and oxide capacitance is related to a dielectric constant over the thickness. So one possible way is to increase the transient performance, for sure we decrease the thickness. But if we decrease thickness, we face the current issues, the leakage current issue. But on the other hand, we can find out if we increase the dielectric constant, then that means probably we don't need to further decrease the thickness because we can keep the same thickness, but we still can make the transistor has a higher output current. So that's why we need to have the high K dielectric as well. So here is some of the more experimental results. So the direct tunneling is a major limitation for scaling of oxide thickness. So that's why we introduce a high K dielectric. It becomes necessary. And this is the left hand side. This is a transition. In the thick dielectric, we have FN tunneling, but now we go thinner. We have the direct tunneling. So this is a nice graph to illustrate this transition. And also, we have another issue. That's what we call the bulk limited conduction. The bulk limited means that this is the conduction inside the bulk material here. So this is a case when dielectric with a larger shallow trap density here, and therefore the current conduction is not limited by the electro injection current anymore, but is mainly limited by the defect here. So if we have the huge defect in our dielectric here, then electrons inside here can start to move here and jump to the one shallow defect and jump to another shallow defect, and that's the cause this kind of a tunneling to the other side. And also the trap energy for this defect is small. So that means the electron can easily go through the dielectric by this defect. And in this case, no matter how large of your dielectric, how thick your dielectric, it doesn't matter. It's always limited by the bulk conduction here. And this is generally we call as a poor Frankel emission, because we have a defect that can start to help us to do this conduction here. And the current is strongly temperature dependent, so we can see there's a temperature factors inside this equation. So here is a summary for the conduction process in insulator here. So we have a FN tunneling that's already mentioned. This is due to the triangular barrier. And we have the direct tunneling. This is because very thin dielectric. Also, there's a very traditional one called the Schottky emission. So it's mainly that the electron need to get enough energy to overcome the Schottky barrier. That's what we call the Schottky emission. We also have this poor Frankel. That's because due to the defect, the trap, shallow trap inside the dielectric. And the last one is also, sometimes we have this, what we call the hopping conduction, because of if we have too many defects, so the electron can be hopped from one side to the other side. So this is some of the slide. Also, it's the same. Just try to summarize. And then the main difference between this and this is a slide that I copied from the very long old history, very long old literature, but it's very classic, very epic literature, but the quality of figure is poor. And this is a slide come from the student presentation. So this is just an example that for your presentation task, you can use my slide for sure, but you can improve that, become the way that more comfortable for you to do the presentation. This is just the student presentation slide a couple of years ago, because I found that they made a nice graph even better than my original slide. That's what I hope to have. I admit the slide, the lecture slide, I proved it there because there are lots of so many old literature. Then this literature, sometimes the figure quality is not that good, but the point is that that can give you the good motivation to improve them, become your own thing. So that is one example. So in this slide, it's very clear, but the conclusion is same. So if you have a scene, then you have FN tunneling, this is a case with roughly 10 nanometer, you have FN tunneling, but if it comes to very thin, you have the direct tunneling. Okay, so the next one is a hard carrier injection. So hard carrier is also one of the very well-known issue nowadays in the advanced semiconductor technology because of the bias we apply here will easily to induce a hard carrier injection. So hard carrier is the carrier that has gained large energy in the high electric field. So that's what we call the hard carrier here. So once electrons under the certain status, then we apply the electric field, and then the electron will gain enough energy, and then the electron will start to jump over this barrier and reach to the other side. So this is how we call the hard carrier injection. So hard carrier can be generated by large fields in the channel, so that's what we call the channel hard carrier, or large field in the depletion region here. So not only what we call hard carrier is actually implies not only the electron but also the holes as well. That's only purely depends on our electrical field. So this is one of the results that come from the hard carrier injection. So when we talk about the hard carrier injection, is a condition where the device is turned on. So we have a VG is larger than threshold voltage, and then our channel is on. So that's why we call this on state. So during this on state, we have the huge electrons inside the channel. But on the other hand, we apply the drain bias where it's larger than gate bias here. So because of this large drain bias, if you look at this, is the electrical simulation curve from the TK. So this is source side, this is drain side. So we can see in this case we have the high peak electric field in the drain edge here. So this is a high peak E field, and therefore this will have the huge energy for the carrier here. So now you have the huge electrons trying to flow from source to drain. By the meantime, once it reach to this region, we have the huge electric field. So this huge electric field will try to push the electron being injected upwards. So here, that becomes the hard carrier injection. So then you will see that in the gate, near the drain side, the dielectric will be injected in the huge amount of electrons. So that's what we call the hard carrier injection. So the hard carrier injection will also cause this is electron, will cause the threshold voltage shift and drain current decreases. This is an issue getting more and more serious recently. You can see this is the paper who first to publish in the hard carrier is a very long time ago. It's older than 1985. That's already observed. So at the moment we have pretty old semiconductor technologies. But if you look at the hard carrier injection, you put it in the Google Scholar, you look at for last 5-year literature, you found out that these effects even get more crazy nowadays in our advanced technology, because in our advanced technology, we have a shorter channel, we have a shorter distance. So in that other word means that we have a higher electric field. The high electric field always gives us a high energy to our transistor, to our carrier inside the transistor. So that causes the serious problem of the hard carrier injection. This is another illustration that the hard carrier injection. So we have the high electric field in the drain side. So a large electric field at the drain lead to the high energetic carrier generation. And as I already said, nowadays we try to scale our channel length. We make our channel length smaller as possible, and our lateral E field is increased. So lateral E field is increased. That means our hard carrier injection is increased. So you can see this is also another evidence that why reliability is important, because of these all the issues what I have mentioned so far today. These all issues have been already discovered more than 30 and 40 years ago. But nowadays it's getting pretty complicated and more challenging because our technology is moving to another level that will keep driving these issues. Okay, so we have several, because now we know there's always the trapping issue, there's a charge injection issues inside our semiconductor. First, we realize there's a phenomenon. A second point is we need to know how to detect, how to estimate, how to measure, how to characterize this effect. So there's several standard effects, techniques here. The first one is the CV, which is the most popular one. That's very, very important. The CV measurement is mainly, when you first time to listen, to understand the CV is mainly come from the semiconductor physics. We will talk about how to form accumulation, depletion, and inversion. And that's also important to understand how the MOSFET operation is there, leading to understand how the MOSFET. But those knowledge are more important, not only understand MOSFET, it's more important to that we can apply to understand these trapping issues. So we will talk about the high frequency. There's several techniques: high frequency CV, low frequency CV, quasi-static CV, conductance method. So we will briefly go through this method one by one. Of course, in this class, due to a time limitation, we cannot go each one in very detail. And also just want to let you know that many of the researchers, they been working on one specific topic from his PhD till after becoming a really experienced researcher. For example, the hard carrier injection. Hard carrier injection is already the topic that you can deep inside for more than 10 to 20 years. But we only have one or two lectures for this, so I just quickly go through. But I think it's good for the graduation courses, we should not go too detailed for each one, because this is a different way compared to the undergraduate class. Undergraduate class, everyone expect professor, lecturer have to talk the equation in very detail, have to give you some example to teach you how to do the mathematical calculation, to teach you how to solve the homework. But to be honest, in the graduate course, I think the main purpose is to push you have the capability of the self-learning. If you are interested in this class, if you feel this class information will be useful for your future work, you can learn from everywhere. There's so many online resource books all talk about this. Anyhow, all the information here are pretty old. This information has been already discovered for more than 50 years. So ideally, there are so many online resource, free resource you are easily access. So I encourage you everyone, if you are interested in one of them, for sure you can first to get the pretty basic understanding from my courses, and then you can do your homework to understand more, because this will help you to have a more correct mindset for the self-learning, because in the future you need to do the self-learning. You cannot expect that everyone will teach you hands with hand for everything. Okay, so the next one is substrate hole slope technique. This is also very popular. It's mainly we estimate the substrate slope to look at the DIT. And there's a technique called DLTS. There's a technique of the charge pumping. So that's all very famous for the techniques. One of the learning philosophy I have also leading to my teaching philosophy now is also, I believe that the less is more. Less is more. It means that if we teach too much, sometimes it will confuse you. It will try to make you feel that, wow, this is so way too complicated. But sometimes less is better, because we just teach the basic part. If you feel interested, you can look up by yourself, and that is completely driven by your own motivation. That is better than in the class I try to teach everything in detail, but sometimes that you will feel completely overwhelmed. So less more is a nice strategy, not only for the teaching, also for your own learning. So I think that's a good quote that you should time to time think about, especially in nowadays. I think the information around us is like overwhelmed. Everyone who try to have absorb so many exploding information, and then sometimes this exploding information might confuse what we should do in the next and influence our decision. So try to keep the less more can simplify your mindset. Sometimes good to make your mind a little bit calm down and a little bit relaxed, and little bit to have some patience, take time to make the good decision. Okay, so when we talk about DIT techniques, we can divide by the type of device that we can use. The first one is a MOSFET, and second one is a MOSFET. So MOSFET is indirect. So because we cannot, there's an indirect or direct based on the MOSFET. So we will use a low frequency or quasi CV or high frequency CV, and also direct is we can estimate using the conductance or capacitance DLTS. In the MOSFET, we can use the substrate slope, and then also in the MOSFET we can use a noise or charge pumping. And some of these we will quickly mention in the later on, for that you have a rough understanding of what actually the key idea for these techniques. So the first one is capacitance, the DLTS. That's the full name is called the deep level transient spectroscopy. So it's a very complicated name, and then its idea is what we try to look at the trapping level happening in the transient. And the DLTS was developed really long time. So that's the technique developed by 1974. But nowadays we still very often use. So you can see this should be the very reliable techniques. So to investigate energetically deep charge trapping levels in the semiconductor space charge structure, which either could be p-n junction or Schottky barriers here. So the idea is we have the one, let's say, for example, PN junction. So as you all know, inside the PN junction will naturally form the depletion region or space charge region, which is here. So we have this depletion region, which is related to our bias, our doping concentration in the P region and N region, and this will form the capacitance here. So idea is to measure the capacitance transient at a different temperature in the semiconductor space charge region. So this is the equation for this one. Then we can start to apply the Arrhenius plot and also allow us to calculate the activation energy here. And one thing I also want to mention that as already been mentioned in the first class, reliability overall is a very practical engineering thing here. So of course there are so many theories behind, but my experience is that I know the DOTS for a really longer time before, but the real feeling that I start to feel like I finally understand the DOTS is I start to do the DOTS measurement. I start to characterize DOTS, I do the DOTS, I try to analyze the DOTS result. So it's very normal you feel confused, the knowledge we learn here. You're confused about the equation, you're confused about the later on the procedure. It's fine, but just try not to give up because of this information will be useful once you need to practice on your device, because this all related to the real measurement. This only will get more sense and experience once you really conduct the similar measurements. So here's what I say. If you want to do the capacitance DOTS measurement, this is a typical waveform, what we have to consider. The first stage is what we call the field trap. So the field trap is, first of all, if we have the one PN junction here, we have a one PN junction device, and then the first step is that we know possibly we have a defects inside. So first of all, we possibly have a defect in this region, but we want to see how this defect will influence our characteristic. So what we should do is we have to fill the trap. What does mean the fill the trap? It means we start to give the bias and start to have the electron flow. Once have the electron flow into the defect, for sure, electron will start being captured by this defect as well. So this will cause the electron trapping. And the black one, this is defect. So the idea is that we know there are some defect in our PN junction, but we want to make sure this defect can influence our result. So first things we try to intentionally to fill the trap as shown here. So that's why we give a pulse here. This is pulse, try to induce the electron and the electron will allow this defect start to capture the electron, and that's why we have electron trapping here. So this is field trap here. And after the field trap, we start to move to the second phase, where we don't give the bias. This is no bias region. So once we don't give the bias, we can expect our PN junction here. P and N. We all know we have the defects here, right? And we also know the defect now is capture the electron. But since this is the moment we saw the bias, so this electron might start to be in the process of the detrapping. So we can start to foresee this electron detrap. And we all know there's a capacitance here due to the depletion region. C depletion capacitance. But this capacitance will the capacitance, depletion capacitance mainly depends on the depletion width. And depletion width is highly correlating to how many charges inside. So once we have detrapping, that means we will influence our depletion width. In the end, influence our capacitance. So depletion capacitance is definitely certain correlated to our detrapping here. So now we can see in the second phase, we saw the bias, the capacitance is changed because we have a certain of the charge is decreasing inside the PN junction. So we can expect this charge decreasing charge inside the PN junction will cause the influence on the depletion width, in the end cause the change to the depletion capacitance. So the capacitance will gradually change here. So now the idea for the DOTS can be simply just considered as a two phase. The first phase, we try to push, we intentionally to induce a trapping effect. At second phase, we let the device to have a detrapping. So probably, if you still remember a bit like probably 10 slide, 15 slide before, we talk about the threshold voltage, we talk about recovery, we talk about the things relating to permanent degradation. We also use a similar concept. We try to stress, we see the threshold voltage shift, and then we let them rest. We don't give any bias. We see the threshold voltage, whether it can be recovery or not. And we use this recovery characteristic to understand the defects characteristic, to understand defect property. So that's the whole mindset inside the DOTS. So now, if we look at for the different temperature during the detrapping phase, we can expect high temperature give us a fast detrapping, and medium temperature and low temperature give us a very fast, very slow detrapping. This is as a temperature increase. Since now we have the temperature dependency, now for sure we can start to apply the Arrhenius plot. So this is the reason we learn the Arrhenius plot, because this is the moment we need to have the Arrhenius plot where you have the detrapping time, you have the capacitance recovery time versus 1 over temperature, and we can start to plot the 3, and then we extrapolate the activation energy, and this activation energy indicates the energy level, the trap energy level in the p-n junction. Okay, so that's the idea for the DLTS. But if you try to look at DLTS, sometimes there's one book just complete talk about DLTS. But I really try my best to use 2 slides to pretty easily to explain the idea of a DLTS. Of course, there's some of the additional, but that's pretty enough. The idea for DLTS is already shown here. Okay. So related to the interface trap, that's also we can consider to give the different bias to induce the trapping or detrapping. So this is a bias under the VG, and this is a Fermi level is here. So I already showed in the previous slide, we talk about the acceptor, we talk about the donor. We actually consider the same concept. If you have the state below EF, because the electrons are a lot in the state below the EF, so therefore the electrons are easily access this defect, and then that's we see this is a dark, the black bar here, that means it's trapping. And once we give the gate bias larger, so actually start, EF is still here. This is our Fermi energy. But now it's getting more interface being trapped by the electron. So this is the trapping. Also, we consider the negative bias here. So now our EF is here. So your negative bias only have the one state below EF, and the rest are empty now. So that's why this is detrapping. So in the end, you found out that I hope everyone can have a feeling that everything is very consistent, no matter in which way you try to understand. You can understand in the pure like the defect and moving in, moving out. Use this schematic. You can also understand the trapping, detrapping, or use the Venn diagram. You can also understand the trapping, detrapping as well. So the trapping charge can lead to a shift in the flat band voltage, but also lead to the stretch out of our CV curve here. So now you can see this is a high frequency CV, this is a low frequency CV here, and then this is a case when DIT is equal to 0. But when we have a DIT here, we start to see the stretch out of our curve. So the DIT increase, so CV curve has a stretch out. And also, this is another, once we doing the stress, we can see the CV curve will change as well, as shown in the bottom figure as well. So that's why we can start to have the good, like the feeling that probably we can use a CV to estimate our interface trap, because the interface, once we have the interface trap, then the CV will change. So the first method we use is called the low frequency, or we call the quasi-static method. So the quasi-static method is basically by consider we have a low frequency capacitance here, and then the interface state density is calculated as shown here with a low frequency curve. So that's a low frequency method here, and then the DIT here can be estimated down to 10 to 10 here. So if you are interested to know this equation come out, I recommend it for this textbook. This textbook is pretty useful. It's kind of like the tool book for me, even for right now, because this book is all combined, all important characterization method from the materials, electrical, whatever defect, everything. They all include everything. So you don't have to read all of them, but this book is like the dictionary. It's like if you need it, you go there, you definitely will find something, information you need. And next one is a conductance method. So the conductance method is also the very old one. It's proposed in 1967, but the conductance method is still very useful nowadays. If you look at the Google Scholar, you found out that many nowadays people still using the conductance method, and then the trap density can be down to 10 to 9 level. So that's very low. So you can see the idea to use the conductance method is considering that if we have the network, this is a very simple network that we consider as a MOS capacitance. So we have the dielectric will contribute our CX, but we also have this is a substrate capacitance. But now if we have the interface state, then the interface state will also contribute this part, which is interface state resistance and interface state capacitance here. To simplify this issue, we try to use another GP that we call the parallel conductance to model this one. So this is a GP that we call the parallel conductance. So the first step is we propose to use parallel capacitance and parallel conductance to modeling this and this. But in reality, if you do the CV measurement, you will understand, you will not be able to distinguish this and this, because you only measure the electrical signal from the top. So the information you will measure is a total capacitance versus a total conductance. That's all. So this is a real measure result. Because in the measurement, there's no way to distinguish. What we can only do is do some mathematical calculation. So then we just try to equilibrium this network to equal to this one. So if you try to put these two will be identical to each other, then you can start to convert the GM here to this equation. So the GP over omega is equal to this over this here. And then the GP here, this is parallel conductance, is related to our measure conductance and measure capacitance here. And then omega is equal to 2 pi f. So that means this is frequency related because we have f there. And CB is the ideal capacitance here. And with considering some simplified calculation from this to this. So once we have a GP over omega, so we can put them here. Then we have a DIT will be roughly equal to 2.5 times GP over omega. And in reality, since this is a frequency dependency, so what we really do in the conductance method is we will measure the G. This is G over A omega Q, so that's exactly this one, GP omega. And the reason why I have the A omega Q because it's divided by the area, but divided by the charge. But anyhow, it's just related to GP over omega is equal to this one. And with the frequency, because we know the GP is related to frequency, then we can start to see the different frequency response here. And then we will start to calculate the peak from here. And why we will extrapolate the peak here is because the peak here is an increase or decrease. So that means the peak is a moment that frequency can cause the trapping and detrapping with an equal rate. So that means this is a frequency that we are interested to characterize the energy level here. So now we have the frequency. So we have a frequency, we can convert, you know, the frequency can be converted to the time constant. And also because 1 over frequency equal to t, so t is a time constant. So now we can convert this to the tau here. And also by consider this equation, we can start to make this one. We can start to make this graph. So we can realize that each different energy level here, because the x-axis is the energy level. So now we have the tau is here. We have an energy level here. So ideally, as long as we have a tau, we can have the energy level. Of course, this equation is very complicated, so usually we make the graph like this way. So now, if we look at this value of the DIT, which is estimate from here. That gives us a 0.43 electron volt. So we then correlate to this energy level. So this DIT is from here. So DIT is equal to 2.5 times GP over omega. But the x-axis, how do we know this DIT correlated to energy level? We have to consider this one, compare to this graph. And then we have the time constant here that can correlate it to the energy level. That's 0.43 electron volt. And then in the end, will come back to here. So you will have the chance to practice this in the homework 3. In homework 3, you will have a chance. We will provide some raw data for the DIT, so you can estimate, try to estimate the DIT by yourself. The first time to run this method is a little bit painful, but once you go through once, you will understand that it's just not that straightforward, to be honest. The method here is not very, very straightforward, but once you understand, you practice once, I believe you will remember it for your whole life. Okay, so I probably will stop here and we'll continue to the next week. So next week we'll start to talk about the charge pumping. That's another very classic method. And also just want to make sure that because of some of you not here today, I just wonder, does anyone who know your group member? If you don't know, you can come to talk to me. I will help you to find your group member. If you already find it, please start to work on with your group member for the presentation. So anyhow, I put all of your name in the upload material already. And then as far as I know, you can also find it in your email in the E3 for your group members, the email. But if you still cannot find it, just let me know. Okay, so we will see each other next week.